We are very honored to have Guna Ponnuvel to speak to us. Guna Ponnuvel is the Director of Product Engineering at NVIDIA, responsible for bringing up and qualification of chip and board products. Guna has worked on leading-edge technology for 15 years, innovating many silicon process optimization, test productivity, and quality improvement techniques to enable low transformation cost and high-quality commercial and automotive products. Prior to joining NVIDIA, Guna was responsible for the bring up and qualification of Connexion's central office and customer premise equipment chipset products. He holds a bachelor's degree in electrical engineering from Bharatiya University in India and master's degree in electrical engineering from Illinois Institute of Technology in Chicago. The title of his presentation today is Machine Learning in Advanced Automotive Quality. So help me to welcome Guna Ponnuvel.
Thank you very much for the introduction. So I guess my colleagues had a different variety of thoughts on application of AI and more importantly the difficulty of processing large volumes of data. And here is a real case where we do process large volumes of data to improve the quality of our product. So here are the different topics we're going to cover in this talk. Automotive mindset, complex car electronics, and the complexity around the supply chain. And to kind of go over the advanced topics, I thought that we should touch base a little bit on the basics of automotive quality. And so a couple of advanced topics, and then we'll summarize what the vision is and what the conclusions are. So, what is automotive mindset? I'm sure whenever you guys who are the new company that's getting into automotive, they always put this famous word. Hey, you should have automotive mindset. Hey, design guys, you should have automotive mindset. Well, there are different ways of explaining what automotive mindset is. One way is to look at the cost and the implication of a failure. If you have a failure during the manufacturing of a chip, it costs us tens of dollars, maybe hundreds. But once you build that chip into a system, that costs us hundreds of dollars when you encounter failure. But now, when you install that system into one of the expensive cars, and you encounter failure and you want to replace that box, that's going to cost $10,000. One of the BMWs to a dealer to upgrade a software, that costs close to $5,000 to $6,000 for BMW. And more importantly now, as the industry is moving towards autonomous driving, it's not only the cost at stake, it's also somebody's life at stake. And what's more important, that's really the key point. That's what drives us to continuously look for opportunities to improve quality. And here comes machine learning as a tool. Complexity of car electronics. Your car is going to be one of the most advanced computer, and it is happening as we speak. It's got 140 plus embedded processors, 100 plus sensors, 1 plus mile of cables. I guess it's already reaching 2 miles now, and 100 million lines of code and still growing. Just in contrast, the Boeing 787 has 7 million lines of code. Now, given the complexity of this electronics, industry needs tools to manage them. And that's where the automotive basis comes into play. Now, we also know that the automotive systems has multiple components from different parts of the world, which makes the supply chain very, very complex. Here's a picture of it. You get PMICs and diodes from one corner of the world, DRAMs from Korea and other parts of the world, and SoCs from Taiwan, primarily supplied by the Tier 3s. Then they get assembled in a board. It either happens in China or Taiwan or somewhere in Asia. Then the board gets shipped to Europe, which gets put into a box, into a system. That's where the system assembly happens and testing happens after that. And then it goes to the car assembly factory, either the one in Fremont or anywhere, any part of the world, and they install that and they run a testing. That's called 0 kilometer testing. Then after the testing is done, then they get into the cars and then they start driving down the streets. This is how complex the supply chain is. Again, we need some tools to manage the complexity of supply chain as well. And here comes the couple of tools that's heavily used in the industry. APQP and PPAP. APQP stands for Advanced Product Quality Planning. It helps all the different suppliers in the automotive industry to develop auto products, auto quality products. It's not just products, it's auto products. It includes all the quality attributes. You can see FMEA, SPC, MSA, PPAP, some sort of APQP. We'll dive a little more details in a second. It also provides guidance for all phases, all the way from requirement gathering, defining the concept, designing, validating, qualifying, and releasing to production. It just serves as a Bible for bringing up a new product. It also standardizes the ways of sharing data. For example, we don't want a PMIC supplier to be showing a data in a different document versus a DRAM guy from Korea. They should have a standard way of presenting the data to show, for example, the SPC controls. So that as a tier 1 or a car OEM manufacturer, they can look at the scan through the data and find out where the potential hiccups are. PPAP is production part approval process. It helps to establish confidence in supplier and process. As a tier 1 or a car company, they want to have confidence on all their suppliers. And that whole process helps them to build that confidence. Accountability through formal approval process. So each of the change goes through a very formal approval process and it gets clearly documented. So when things go bad, they know how to backtrack it. And this also serves as a process to satisfy the requirements. As you know, the requirements for each of the components is well defined ahead of time, and each of the suppliers, as they go through the process of qualification and productization, they have tools to confirm that particular component has satisfied the needs. Now, on the advanced topics, there are quite a few topics that we can touch base on automotive quality advance. But I would like to touch base a couple of them here, given the time consideration. So, one of them is high quality at affordable price. And the second item is manufacturing relationship. As I just showed, the global supply chain is pretty complex when it comes to automotive electronics. And as we dive into the details, components are always more expensive, and especially the SoCs and the processors. End customers' quality standards are ever tighter. I've had customers move from DPPM to DPPB. They want, defect per part per million to be reduced to per billion. And that's a substantial tightening requirement. Extra testing can improve quality, but brings cost. And that's where machine learning, we're going to use machine learning to stress the parts that needs some more test. You don't want it to throw out 100% of the parts to test 100% of the time, but rather you identify the right parts that wants the right amount of testing. Now, when it comes to the supply chain complexity, solving problems across company lines can be difficult. Barriers like, for example, in the previous slide, we saw PMICs and diodes coming from another corner of the world compared to DRAMs in Korea, SoCs in Taiwan. Just communicating with all of these suppliers, it's the biggest challenge, and it just delays the debug process. And the idea here is we want to enable a chip ID exchange, like how each of us have a tag on our shirt. The idea is each of the components should have a tag to identify without sending back to the supplier. So why machine learning and quality? One would wonder, okay, there's a lot of data to process, but our view is the question that we keep asking ourselves: should we always test 100% of chips to weed out 0.01% or lower percentage of bad parts? And on the left side, you see an overlaid wafer map of 250 wafers of one of our product. The question that the dark red color are the dies that, this is just a quality grading of all the dies of 250 wafers on a top view. Just looking at it, the question that we ask ourselves, hey, looking at the quality level of all these dies, do we need burn-in for all of them? The answer is no. I mean, if you look at their dies on the white space, they are the highest quality die. Why do we need to stress test them when the quality level is so high? Whereas the dark red, those dies always need extra testing because there is still a bit of a concern from the quality level. And the light red ones, not all the dies across 250 wafers need some additional testing, but some of them they do. Now, how do we identify or differentiate or classify these type of dies? That's what leads to per chip prediction. What's important? In our manufacturing test process, all the way from foundry to different levels of test at wafer level and package level, we generate lots of data. We generate thousands of records per die. And as soon as we get all these capability from all the descriptions from our colleagues, we should be able to process those thousands of parameters and start developing a model. And that will allow us to then develop a model that will reduce the number of data records needed for the model to say 50 in this case, or even lower. So it's a small percentage of all the different data sets that we've generated that we use for real-time storage. And then we can use a slightly larger set of data to kind of keep monitoring the accuracy of the model and continuously improve the model as we progress. So the important thing about machine learning is not just arriving a model, but it's very important that we have to have this continuous feedback at regular intervals and keep fine-tuning the model. Here's a simplistic view of our manufacturing test flow. On the left side, we start with wafer acceptance test that's done in our foundry, and that gets into our database. Chip probe 1, chip probe 2 are wafer level tests done at different temperatures. And they go through some sort of wafer map merge, and then go through assembly, final test. Then we have some burn-in, and then do final test post burn-in, and then we ship it to customers. If you see that, all the data gets fed into this database and gets stored here. So the amount of data that we generate just from CP1 and CP2 is already, greater than thousands of records per die. I think we are heading in the direction of tens of thousands now. So the idea here is, given that all the data gets centralized in the database, we should be able to develop a prediction engine that can classify the dies that are high quality versus moderate quality versus slightly low quality. And once we are able to classify those dies, then, some trouble with the laser here, but you could see that the best quality parts on the right side, they get shipped right after FD1. But as the other parts that are suspected to have lower quality, they go through this burn-in or stress testing, then do a follow-up insert, and then before we ship to the customers. The most important thing to note here is we do have continuous learning, so the model gets updated and retuned. As the process moves around in the wafer, the test results adjust accordingly, and the model sensitivity has to be taken into account. So this is kind of like a simplistic view of our application of machine learning for improving the quality of automotive. So a view of how the prediction engine works. I guess it's a little bit of an overview, but the idea there is on the left side, on the left chart, you see the x-axis is percentage of dies that were sent to burn-in, or qual testing, or additional testing. The y-axis is additional follow-up to PPM. What we do is we first develop a preliminary model, and then we go through the learning phase. During the learning phase, 100% of the chips go through the extra testing or the burn-in, so that we can keep fine-tuning the model. Our goal, our more efficient model would be when this particular curve moves to the left and down side. Ideally, we wanted to come back somewhere on the left side so that you have minimum number of dies going through burn-in and you get most benefit out of it. So now let's talk about the next topic, the manufacturing relationships. As we saw in the global supply picture, there are many companies involved in the process of building an automotive system. And we need an efficient way to kind of enable the communication. If you look at an IBM model, the IBM owns all manufacturing data. Right? They have the silicon data, they have the design data, they have the test data. So the integrated device manufacturer owns everything. So that's the easiest way of getting all data to kind of run the correlation analysis, do any debug on any failures that happen. Then comes the fabless foundry model. In fabless companies, the companies have control of the design data and the test data, but the silicon data is still at the foundry. So it's a little tougher, but not that tougher. We can still partner with our foundry team, run through the correlations without actually having the units physically in hand. But the next step is when you have a system or a board where you have multiple components that you're buying from different companies. The customer failures, or the failures that happen in the customer side on the field, it's a small pile of failing dice. I mean, it's like hardly in DPPMs. You're talking about, a few DPPMs on memory, a few DPPMs on SLC. So if you start looking at it, those type of failures, first to debug, it becomes very strenuous and has a very long cycle time because the parts have to be ripped off from the board and has to send to the supplier to kind of retest, identify what that unit is to run the correlation. So this whole effort is pretty complex, and it takes a long cycle to run all the statistical analysis to identify the cost for failure. Problem statement, working with component suppliers is inefficient because we have so little data to show the problem exactly. So our proposal is every chip has a name, like how we all have a name, and also now we have a tag to kind of have everybody else know who we are. The hard way is basically what is most of the time happens is we get the boards that are failing from our customers, and what we do is we rip off the component. We try to isolate the component of the board, which itself is a pretty complex effort. The moment we identify, we have to rip the component off. We have to physically send back to the supplier. It could be somewhere in Asia, and it takes the transit time, not to mention with the custom clearances, and that delays the overall process of correlation and identifying the cost of the problem. The more longer we take to root cause a problem, the more parts are going to go out that could potentially fail for the same problem. So it's important that we identify the problem and contain it as soon as possible. The proposed better way, on the right side you have an example there. So we have component 1, component 2. Our suggestion is we should have an option where you could read, we have the ability to read the electronic chip ID of that component, and then you could, most of the time it's scrambled, but at least we can send back that electronically to our customers and have them give us the actual unscrambled value for us to run the correlation analysis. So our suggestion is get boards with failing components, extract ESET, electronic chip ID from the board, send to force back, correlation analysis. While that's happening, then you can have you make the slides, have the meetings, and try to go through the root cause process. Now, here's a view of our mission. This is kind of the same slide where we showed the complexity of global supply chain for automotive electronics. We want machine learning at each factory to improve the quality. If each of the suppliers can apply machine learning to improve the quality, the overall quality of the system will just improve. And that's even more critical with the autonomous vehicle coming into play now. The next step is we want unit level feedback when components fail. Like if a system in a car fails, the car company should be able to read the ESET that's causing the failure and should be able to percolate all the way back to the tier 3 suppliers. Here comes the last slide, summary. So in summary, you're going to use machine learning to rank the silicon according to predicted quality, apply additional stress testing on the chip that needs the most, improve the models over time. That's the most important part. We got to keep learning and continuously improving the models so that the accuracy retains the same level. Suppliers of expensive components are partners, they're not adversaries. Supplier-customer problem, the needed data are divided out. Different pieces of data are in different parts of the world, and we need a way to break down those data barriers and have easy communication. That's where electronic chip ID comes into play. Failures are connected all the way from the field to the factory. And there should be an easy way to communicate to behave in each of the component, and that's where the chip ID is going to help.
Thank you, Guna. Well, since we're talking about, since Guna talked about quality and test, so we decided to have Guna to be our first speaker to test our high-tech Q&A session, where we already collect quite a few questions through WeChat group real time as Guna was talking. So let's give that a try. The one. Okay. Would you be able to give the latest AI training chip performance comparison between TPU, NVIDIA, Intel, and ARM-based chips? Okay.
Good question. Unfortunately, I'm not a marketing guy to answer that. But whoever has asked this question can reach out to me offline, and I can get you guys connected to our marketing team. And as it is, GPUs are still the best. There's no doubt about it.
Well, that's quite fair. Thank you, Guna. That's, so at this time, we'd like to have Richard to present a token of appreciation to Guna.
I think there's one more question.
One more question? Okay.
Sorry. Go ahead.
Thank you very much for the presentation. So can you go back to the previous slide, which you have the vision listed on the slide? Thank you. So this vision means that it's not happening right now.
I see as a start, we guys have started applying machine learning to group quality, and I've also seen a lot of suppliers talking to us and wanting to apply similar processes on their factories as well. So it's kind of in progress, not quite done yet.
Right. So as you mentioned earlier in the presentation, there are so many layers of the manufacturers and also component provider, right? What would you think is top one priority? If which level or component level or parts level, which level implement the machine learning model will improve the most of the final product at this moment?
Absolutely at the component level.
And are you guys doing anything to force any standard in your vendor levels?
So I think answer is yes. We have given guidelines for suppliers that we work very closely with. Some of them are learning from our application, and they are kind of putting workflows in their factories. Answer is yes, we are providing some guidances.
And who is bearing the cost, the vendor or you guys?
Absolutely the vendor.
Thank you very much.